So problem 2.1 goes like this. A sphere of 200 diameter made of cast iron, initially at a uniform temperature of 4 degrees Celsius, is quenched into oil bath. The oil bath temperature is 40 degrees Celsius. If the temperature of the sphere is 100 degrees Celsius after 5 minutes, find heat transfer coefficient on the surface of the sphere. Take Cp value is equal to 0.032 kilojoule per kg per Kelvin and density of cast iron as 7000 kg per meter cube. Neglect internal thermal resistance. And this problem was asked in Winter 5 6 marks. So in order to solve this problem, let us first draw the schematic. Now let us first try to understand the physics of this problem. Initially, there is a sphere of some diameter d. Initially, that means at tau is equal to 0. At a uniform temperature of how much? 400 degrees Celsius. As you can see here. Initially, there is a sphere, and particularly this sphere, cast iron sphere. The cast iron sphere of diameter d initially, that is at tau is equal to 0, was at temperature 400 degrees Celsius. Now later on, this sphere was dipped to quench into the oil bath. Let's say the temperature of this oil bath is T infinity and convective heat transfer coefficient is H. Now what happens when this sphere is quenched into this oil bath? There exists temperature difference. The cast iron sphere is heated and oil is cooled. So heat transfer will take place from this sphere to the oil, and its temperature will start decreasing. So what I can say, after some time or at any moment of time greater than 0, what is the meaning of this? Tau is greater than 0. Time after initially, time after initial period. I want to find out the temperature of this cast iron sphere, which will be the function of time, because it is going to vary continuously with respect to time. That is why I will say temperature of this cast iron sphere after immersing into the oil bath will be the function of time. So I want to find out what will be this temperature. Correct? So this is the schematic of this problem. And this way you are supposed to represent the parameters involved in transient heat conduction. I have represented the diameter. What is this object? It is a cast iron sphere. Here geometry is important, whether it is a sphere, cylinder, plate or cube. So I have clearly mentioned it is a sphere. Tau is equal to 0 means initially its temperature was 400 degrees Celsius, and after quenching, temperature at a particular time tau is a function of time. And title of this figure will be quenching of sphere by oil. Okay. Now let us enlist all the given parameters. So as you can see here, there is a sphere of 200 diameter. So its diameter will be 200 0.2 meter. Therefore, its radius will be half of the diameter, 0.1 meter. Initially at uniform temperature of 400 degrees Celsius, so notation wise Ti is nothing but 400 degrees Celsius. The oil bath temperature is 40 degrees Celsius. So the surrounding to which the sphere is exposed later on is having the temperature 40 degrees Celsius. If the temperature of the sphere is 100 degrees Celsius after 5 minutes, now what is this actually? We have dipped this sphere into this oil bath, and after 5 minutes, that is tau is equal to 5 minutes, its temperature was found as 100 degrees Celsius. So that is the final temperature T, 100 degrees Celsius. And what is the time we are considering? 5 minutes. That is equal to 300 seconds. What you are supposed to find out? Find heat transfer coefficient on the surface of the sphere. That is, you are supposed to find out this H. Other properties of this sphere are also given, like Cp value is given 0.32 kilojoule per kg Kelvin. Now see here, the kilo is coming into picture. So convert this into its basic form, 3200 joule per kg Kelvin. And density of this cast iron is 7000 kg per meter cube. Okay, so all these parameters are given. Now, while solving the problems on transient heat conduction, it is very much crucial to decide these temperatures. What will be the Ti, what will be the final temperature T, and what will be the fluid temperature T infinity. You have to very meticulously identify these temperatures. If you mistakenly taken one temperature as another, your answer may be wrong. Okay. Now, number 3 as assumptions. Assumptions involved in this problem. So, number 1 assumptions. During our entire heat transfer course, we are talking about one-dimensional heat transfer. Now here I cannot say it is a steady state because we are talking about unsteady state heat transfer problem. Number 2, one assumption is already mentioned, neglect internal thermal resistance. So this will be the assumption number 2. Neglecting internal thermal resistance. What is this internal thermal resistance? It is nothing but L over Ka, and it tends to 0. It is 320. Okay, thank you for correction. Then number 3, See, it is the prerequisite of lumped parameter analysis. If internal thermal resistance is negligible, there won't be any temperature gradient within the body. So as a consequence of neglecting internal thermal resistance L over K, no temperature gradient within the body. That is, at any moment of time, the entire body temperature will be 100 degrees Celsius. For example, what does it mean? The 400 degrees Celsius was the initial temperature of the sphere. It is dipped into oil bath of 40 degrees Celsius, and after 5 minutes, its temperature become 100 degrees Celsius. So the 100 degrees Celsius will be the surface temperature of the sphere everywhere after 5 minutes. So that is the meaning of this assumption number 3, no temperature gradient within the body. Let's say if I could consider 10 minutes and its temperature was dropped to 50 degrees Celsius, so the entire surface of the sphere has to be considered at 50 degrees Celsius. That is no temperature gradient within the body. That is the meaning of this assumption number 3. Assumption number 4, no heat transfer due to radiation. Whatever heat transfer is taking place by conduction and convection only. And assumption number 5, constant properties of sphere and oil. That is, sphere material is homogeneous and isotropic, and oil properties are constant. That is, its H value are constant. So I can write here K and H values are constant. They are not going to vary with respect to direction and temperature. So these are the assumptions involved. Find. What you are supposed to find in this problem: find heat transfer coefficient on the surface of the sphere. That is, we are supposed to calculate convective heat transfer coefficient H. Now let us start our calculation. Now the very first method come to my mind to solve transient problem is lumped parameter analysis. First, let us recall from heat transfer data book. I am not writing the page number, okay? Because it is varying from data book to data book. For transient heat conduction, okay. So what we are using? Lumped parameter method. And what is the equation for lumped parameter method? I am using notations differently. T minus T infinity over Ti minus T infinity. Formula is same, only notations are different. E to power minus HAS over rho VCP into tau. This can also be written in this fashion. Same thing. Mathematically, both are the same, right hand side. So this is the equation of lumped parameter method. Okay. T is the temperature after any time tau. Temperature after any time tau, and it will be function of time. Rest of the parameters and their notations are very clear. And oh sorry, T and tau is the time. Please do not get confused with these two symbols. So this is the equation by lumped parameter method. But there is a condition associated with this lumped parameter method, and it's equation number 1. What is that condition? This lumped parameter can be used only and only I can use this lumped parameter method to study transient heat conduction problem only and only when this condition is met. What is that condition? If Biot number is less than or equal to 0.1. And what is Biot number? HLC over K is less than or equal to 0.1. So before using this equation, I must check whether this Biot number value is 0.1 less than 0.1 or not. If it is more than 0.1, I cannot use this lumped parameter method. If this criteria is satisfied, error will be only less than 5%, which is well accepted. So in order to accurate the temperature correctly, I must check this value of Biot number is less than or equal to 0.1 first. So as you can see here, Biot number is nothing but HLC by K, where H is convective heat transfer coefficient, LC is characteristics length, and K is thermal conductivity of body. So first check LC. Since this is first numerical, I am defining each and every term. And it is given as volume over surface area. Now what will be volume of sphere? It is nothing but 4 by 3 pi r cube. 4 by 3 pi, and the value of r is 0.1 cube. So someone calculate it. I could also calculate this value, and this volume comes out 4.188 into 10 to power minus 3 meter cube. Okay. And what will be its surface area? Surface area of sphere will be 4 pi r square. 4 pi into 0.1 square, and this area comes out 0.1256 meter square. Please check this. If there is a discrepancy, turn on your mic and convey me. Now we have the value of volume and surface area. So now I can calculate characteristics length as 4.188 into 10 to power minus 3, this is the volume, to the 0.1256. This is meter cube, this is meter square. So I will get this value 0.0333 meter. Okay. So after having the value of characteristics length, now let us calculate this Biot number. Oh, so here what is the problem? Here the problem is that I don't know the value of H, isn't it? I don't have the value of Biot number, so H is not known to me. So what would I do? How would I overcome this problem? I will assume that assuming Biot number is less than or equal to 0.1. Now actually before applying lambda parameter analysis, this condition must be satisfied. Which one? This one. But as I don't have the value of H, I cannot check whether Biot number is less than or equal to 0.1. What I will do, I will assume that Biot number is less than 0.1. And after calculating the value of H, later on I will check the value of Biot number. And if it comes out less than 0.1, that means our assumption was correct. Okay. So assuming Biot number is less than 0.1 in this case, now from equation 1, what is equation 1? T minus T infinity over Ti minus T infinity is equal to exponential of minus HAS over rho VCP into tau. So let us put the formula. T final temperature is 100. T infinity is I think 40. Ti is how much? 400, and T infinity is 40. And this will be e to power. The value of H is to be calculated. Value of surface area is 0.1256 over rho VCP. The value of rho is 7000. Cp is 320 and volume is this much. Okay. So the value of rho is 7000. Volume of sphere is 4.188 into 10 to power minus 3. Yes, 10 to power minus 3. And the value of Cp is 320. This is HAS over rho VCP. We have one more parameter, that is tau, as you can see in the equation 1, minus HAS rho VCP. So all the values I could put, and tau is time. And what is the time we are going to consider? It is a 5 minute, and we are supposed to pick up this value in seconds. So this will be 300. This is the entire value of HAS over rho v Cp into tau. Now you can solve this very easily. So I will directly get the value of H. So I got this value as 446.17 watt per meter square Kelvin. Let me check this value. You people also check this value. Now how to solve this? How to solve this equation, that also I tell you. There is an exponential term. So shift of ln minus, put this square bracket. So you will get the values of, so since there is an unknown term h here, you cannot solve this e to the power minus this parameter. So what you do, you take log of both the sides. This is the final answer, but in between there are so many steps. Take the log of both the side. So this will become 60 over 360, and when you take the log of e is 1. Okay, and this entire term will become minus h into 0.1256 over 7000 into 4.188 into 10 to power minus 3 into 320 into time is 300 seconds. Okay. So what we are doing actually, meanwhile, taking log of both sides. And now when you will solve this, you will get the value of h as, you people also calculate, I am also calculating. Taking log of 60 over 360 will be minus 1.791. Yes, so it comes out 446.17 watt per meter square Kelvin. So this is the answer. I hope everyone got this answer. Now, since this value of convective heat transfer coefficient H is equal to 446.17 watt per meter square Kelvin, we have got from the lumped parameter analysis, considering the Biot number is less than or equal to 0.1. So we have to check. Now we have the value of, we have to apply a check, that is whether Biot number is less than 1, is less than or equal to 0.1 or not. So let us calculate Biot number first. HNC by K. H is 446.17. LC value is 0.0333 and the thermal conductivity of this solid is how much? Thermal conductivity value is also not given. So we don't have any method to check whether the Biot number is less than 0.1 or not. Okay, this is a special problem. I thought it was a straightforward problem, but there is no value of k also given to us. Okay, so this way you can solve this problem by assuming the Biot number is less than 0.1.